In this video, we're going to continue looking at hypothesis tests for proportions, but we're going to investigate a new method for making our decision in step 4. Instead of finding the critical values, what we're going to do is find the p-value. The p-value is the probability of getting a sample statistic or a more extreme sample statistic in the direction of the alternative hypothesis when the null hypothesis is true. The p-value is the actual area under the curve, and this is going to be in the direction of the alternative compared to the test statistic. We find the p-value depending on the statistical test being used. So reviewing the methods from chapter 7, find the probability that z is less than negative 2.89 and draw a picture. So starting with that picture, our standard normal is centered at 0, so a z-score of negative 2.89 is going to be to the left of that. And we're looking at the area to the left of this because we want the probability that z is less than negative 2.89. Now, using our standard normal table, looking up a z-score of negative 2.89, this area is equal to 0.0019, which is equal to the probability that z is less than negative 2.89. This probability would be considered a p-value if we were looking at a left-tailed test. We use the p-value, like I said in step 4, in making our decision. We reject the null if the p-value is less than alpha, and we fail to reject the null if our p-value is greater than or equal to alpha. We will use our calculators to find p-values using a function called normal CDF. You'll go to your distribution menu, which is second, then the vars key, and then select normal CDF. You'll enter the lower bound, the upper bound, 0 and 1 for the mean and standard deviation of our standard normal. A quick note, for a two-tailed test, we must multiply the value from our calculator by 2 to get the p-value since it's a two-tailed test, and we need the area in both tails. So to illustrate what we're talking about, if I've got my curve and I'm looking at this area, we have to tell the calculator to find the area from this point all the way to this point. So let's say that we have a z-score of negative 1.5. The lower bound, again, is going to be some value over here. Now, technically that's negative infinity, but we can't really type that in. So we can go very extreme, let's say negative 999. The upper bound is the negative 1.5. The mean of our standard normal is 0 and the standard deviation is 1. Again, it's really important when we're thinking about lower and upper bounds. The lower bound is the left bound and the upper bound is the right bound, because we always read from left to right. So let's practice finding p-values for a specified test. Suppose that we found our test statistic to be negative 3.14, and we're looking for the p-value for a left-tailed test. So I'm going to start by drawing my picture, and it's a left-tailed test. So this area in the left tail represents my p-value. I know that the z-score is negative 3.14. So using normal CDF, My lower bound is going to be negative 999. My upper bound is negative 3.14. The mean is 0. The standard deviation is 1. So my p-value equals 0.0008. P-values we will always round to 4 decimal places. Suppose we found our test statistic to be 2.45, and it's a right-tailed test. So again, I'm going to sketch my picture. My test statistic is positive 2.45, and it's a right-tailed test, so my p-value is the area in the right. Using inverse norm, now going from left to right, our lower bound is at 2.45, and our upper bound is going to be some really positive number. Just like we use negative 999 for an extreme lower bound, we can use positive 999 for an extreme upper bound. Depending on your calculator, you might be given a menu and prompted for these values. So my p-value in this case is 0.0071. Suppose that our test statistic was negative 1.32. Find the p-value if it's a two-tailed test. So now we've got two tails to the left of negative 1.32 and to the right of positive 1.32. So I'm going to find the area to the left of negative 1.32. Using normal CDF, my lower bound is negative 999. My upper bound is negative 1.32. That is 0.0934 approximately. But because we've got two tails, my p-value is going to be 2 times that. Now that ... is indicating that I'm not going to round my p-value or that decimal before I multiply by 2. I'm going to keep that answer that normal CDF gave me in my calculator and just multiply it by 2. And my p-value is going to be 0.1868. Another two-tailed example. Now let's say we have a test statistic of 2.63. What's the p-value for a two-tailed test? So now we've got both tails, area to the right of 2.63 and to the left. That's technically negative 2.63. But we're going to find the side that's given, so to the right of 2.63. Using normal CDF, our lower bound is 2.63, our upper bound is positive 999. Our p-value is going to be 2 times 0.00426, so on and so forth. Remember, we're not going to round that decimal yet until we multiply by 2. Our p-value is 0.0085. If you were to round that area first, so you would rounding to 4 decimal places, one tail is 0.0043. If you multiply that by 2, you'd actually get 0.0086, which obviously is slightly off. So just be mindful, make sure you're not rounding before you multiply by 2. Now, one last thing. Again, we find our p-value in order to make our decision in step 4. So let's say we were using an alpha of 0.05. What decision would we make in these cases? So in this first example, our p-value is 0.0008, which is less than alpha, so we would reject the null. In the second case, our p-value is 0.0071, which again is less than alpha, so we would reject the null in this case as well. In the third case, 0.1618 is greater than alpha, so we fail to reject the null. And the last case, 0.0085, is our p-value, which is less than alpha, so we would reject the null. Again, our goal is to try to reject the null. That's typically what we want to do. So we typically want a very small p-value so that when we compare it to any of the normal levels of significance, we would be smaller than that alpha and we would reject the null. This table gives a summary of hypothesis testing for proportion. When we're testing for proportion, it is a z-test. That's consistent with the formula for our test statistic and the fact that we're using inverse norm or normal CDF, those calculator functions dealing with the standard normal distribution. Step 1, you state your hypotheses. Step 2, determine alpha. Step 3, calculate your test statistic. Step 4 is all about making our decision, and we've got now 2 options for that. We've got the critical value method, which is on the left-hand side, and we also have the p-value method on the right-hand side. So if I'm looking at the critical value method, I want to first determine what my critical value is. My preference personally is using inverse norm, but you can use table 7. We need to know what type of a test it is, what our significance level is, and then we need to decide what the right sign is. This is all done simultaneously with drawing a picture and shading our rejection region. Then we're going to mark our test statistic on that, and we'll make a decision based on whether or not our test statistic lies inside or outside of the rejection region. If we're using the p-value method, we're going to use normal CDF on our calculator. If it's a one-tailed test, the area that we get in normal CDF is our answer. If it's a two-tailed test, we need to make sure we multiply by 2. And then what we're going to do is compare our p-value and alpha. We make our decision based on the relationship between p-value and alpha. We reject if our p-value is less than alpha and fail to reject if p-value is greater than or equal to alpha. And then our last step is to state our conclusion. So there is or there is not enough evidence to support the claim, and then we'll state H1. An educator estimates that the dropout rate of seniors in high schools in Ohio was 15% 5 years ago. Last year, 38 seniors of 200 withdrew. At alpha equals 0.05, is there enough evidence to suggest the dropout rate has changed? Use both critical value and p-value methods. So identifying some key figures here, we have a percent and 38 of 200, which indicates that we're dealing with proportion. So our null and alternative hypotheses are statements about p. That 15% is our null value, so p is equal to 0.15 is our null hypothesis. And then we're testing whether or not there's evidence to suggest that the dropout rate has changed. So we're not saying that the dropout rate has increased or decreased, we just don't think it's the same anymore. So our alternative is p does not equal 0.15. Step 2, we state alpha. Alpha equals 0.05. And step 3, we calculate our test statistic. I encourage you guys to write down that formula for the test statistic. When we get into the next section, that formula will change. So if you're going through that habit of writing down the formula, you might be more in tune and aware of how those changes are happening. But now let's identify the values of those variables. P hat is 38 divided by 200, or 0.19. That's our sample proportion. P is our null value, so P equals 0.15, and that's again from that null hypothesis. Q is 1 minus P, or 0.85, and the sample size is N. So now we're going to substitute those values into our formula and solve for our test statistic. I recommend pausing here, typing this in your calculator, and checking your answer with mine when you're done. Our test statistic for this problem is 1.58. Remember, we're always going to round our test statistics to 2 decimal places. Step 4, we're going to make our decision. This is a two-tailed test, so we're going to write that down. And this is important for both methods. So I'm going to separate the critical value method from the p-value method. Please make sure in your quizzes or tests that you're labeling which method you're using. So the critical value method, just as a reminder, is based on alpha. And it uses inverse norm. So we're going to draw our picture and setting up our rejection region. This is a two-tailed test, so we've got 2 areas that represent our rejection region. And the area in each of those tails is alpha divided by 2. So the alpha was 0.05, which makes the area in the left tail 0.025, and the area in the right tail 0.025. Using inverse norm, we find that our critical values are negative 1.960 and positive 1.960. We will always round critical values to 3 decimal places. Now, let's add on where our test statistic would lie on this figure. So again, we're centered at 0, and 1.58 is going to be between 0 and 1.96. Since that's not inside that shaded region, which represents my rejection region, we failed to reject the null. Now let's look at how the p-value method would go. So the p-value method is based on your test statistic. And we're going to use the normal CDF function on our calculator. We're still going to start by drawing our picture. And it's still a two-tailed test. We're still looking at the area in the 2 tails, but now the area represents something different. That area is no longer our rejection region, but it's our p-value. I know that our test statistic is 1.58, so we're looking at the area to the right of 1.58 and the area to the left of negative 1.58. Using normal CDF, the area to the right of 1.58 is approximately 0.0571. When I calculate my p-value, though, I need to multiply this by 2, and I'm going to do that before I round. So that 0.0571 was rounded. 0.0570, and then it continues on, is the full area or the most accurate area to the right of 1.58. So my p-value is 0.1141 if I round after multiplying by 2. I want to compare my p-value to alpha. Alpha, again, was 0.05. This value is greater than 0.05. So our decision is fail to reject. As you can see, regardless of which method we used, we made the same decision, and that will always be the case. If you're ever working on a problem and you reject using one method and fail to reject using another method, that means something has gone wrong. So you need to go back and check your work. Now that we have our decision, step 5, we write our conclusion. Our conclusion is that there is not enough evidence that the dropout rate of seniors in high school in Ohio has changed. A Comcast representative estimates that more than 25% of its customers has a service bundle that includes a telephone line. To test this hypothesis, she selected a sample of 100 customers and found that 37% had a telephone line. At alpha equals 0.01, is there enough evidence to support the claim? We're dealing with percentages here, so we know that this is a test on proportion. And the null value is going to be that original value of 25%. The claim is that they think that there is more than 25% of people who use or who have a telephone line bundled with their cable. Step 2, we state alpha equals 0.01. Step 3, we calculate our test statistic. Using the formula as a guide, we can find the values of the variables to calculate our test statistic. P hat is our sample proportion, and in that sample of 100, they found that 37% had a telephone line, so P hat is 0.37. P is our null proportion, or our null value, 0.25. Q equals 1 minus P, or 0.75, and our sample size was 100. Now we'll substitute those values in to calculate our test statistic. The value of the test statistic is 2.77. Always round your test statistic to 2 decimal places. Step 4, we start making our decision. Based on our alternative hypothesis, this is a right-tailed test. And I'm going to use both the critical value and the p-value methods to make my decision. Again, critical value is based off of alpha. And we use inverse norm. Drawing our picture to illustrate our rejection region. This is a right-tailed test, so the area in the right represents our rejection region. And I know the area of that right tail is alpha, which in this case is 0.01. Using inverse norm, my critical value equals 2.326. I will always round critical values to 3 decimal places. My test statistic is 2.77, so if I were to overlay that on this graph, it would lie to the right of 2.326, which puts it inside of our rejection region, which means that we will reject the null hypothesis. Our p-value method is based off of the test statistic, and it uses normal CDF. We start with a picture similar to what we did with the critical value. It is a right-tailed test, so we are still looking at the area in the right tail. The difference is that we don't know the area in the right tail, but we know the value that separates that tail, and that is our test statistic 2.77. The p-value actually equals that area. Using normal CDF with a lower bound of 2.77 and an upper bound of 999, our p-value is 0.0028. We will compare our p-value to alpha. Alpha was 0.01, so this is less than 0.01, which indicates that we will reject the null. We reject the null if our p-value is less than alpha. Otherwise, we fail to reject the null. Now we state our conclusion. There is enough evidence that more than 25% of Comcast customers have a service bundle with a telephone line. A statistician read that less than 77% of the population oppose replacing $1 bills with $1 coins. To see if this claim is valid, the statistician selected a sample of 80 people and found that 55 were opposed to replacing the $1 bills. At alpha equals 0.01, test the claim that less than 77% of the population are opposed to the change. The claim is that less than 77% of the population are opposed. So that identifies one that we're dealing with proportion, and it identifies our alternative hypothesis as well as our null value. So my null hypothesis is that p equals 0.77, and my alternative is that p is less than 0.77. My level of significance is 0.01, and my third step will be to calculate my test statistic. Using the formula for the test statistic, we can identify the value of the variables from the problem. P hat is our sample proportion, 55 divided by 80, which is 0.69. P is our null value from the null hypothesis, which is 0.77. Q is 1 minus 0.77, or 0.23, and our sample size is 80. Substituting these values into our formula, we find that our test statistic is negative 1.70. Step 4, we identify that this is a left tail test because of the inequality in our alternative hypothesis. And we're going to make a decision using both the critical value and the p-value methods. Our critical value method, we're setting up our rejection region. Since this is a left-tailed test, the area in our left tail represents our rejection region. And the area of that rejection region is equal to alpha, which in this problem is 0.01. Using inverse norm, we find that our critical value is negative 2.326. If I layer on my test statistic of negative 1.70, we see that the test statistic, which is greater than negative 2.326, lies outside of the rejection region, so my decision is fail to reject. For my p-value method, I'm still looking at that left tail, but now the area of our left tail represents our p-value. And rather than knowing that value of the area, we know the z-score that cuts it off, which is our test statistic, negative 1.70. using normal CDF with a lower bound of negative 999 and an upper bound of negative 1.70. We find that our p-value is equal to 0.0446. If I compare this to 0.01, which is alpha, our p-value is greater than 0.01, which confirms that we will fail to reject the null. Based on the decision we made in step 4, we can write our conclusion, which is that there is not enough evidence that less than 77% of the population oppose replacing $1 bills with $1 coins. The last thing we'll look at is hypothesis tests and confidence intervals, and this is only for two-tailed tests. You guys should read these pages in your text. Essentially what this is saying is that we can also use a confidence interval to make a decision, just like we've used the critical value and rejection region or the p-value methods. When testing a null that p equals our null value versus an alternative that p does not equal the null value, so again, this is just for two-tailed test. If our confidence interval contains our null value, we do not reject the null. If the confidence interval does not contain the null value, then we conclude that it's not true and we will reject. Again, to summarize, if the confidence interval contains the null value, we fail to reject. If the confidence interval does not contain the null value, then we reject the null hypothesis. A June 2007 study conducted by Students Against Destructive Decisions revealed that 37% of teens aged 16 to 17 text while driving. Does a 2009 study by Princeton Survey Research Association International, which found that 272 of 800 randomly selected 16 to 17-year-olds had texted while driving, provided evidence that this number has changed since 2007. Use a 95% confidence interval. So our null hypothesis was that our proportion is equal to 0.37, and our alternative is that that proportion or that percent has changed, so p is not equal to 0.37. If we were to calculate our confidence interval for the proportion of teens age 16 to 17 who text while driving is between 0.307 and 0.373. Because our null value is inside of our confidence interval, we fail to reject. Since our decision is failing to reject the null, we can write a conclusion about this test that there is not enough evidence that the percentage of teens aged 16 to 17 that text while driving has changed since 2007. Make sure you also read testing hypotheses about a population proportion using the binomial probability distribution. This is the case if our n times p times q is less than 10, which on our quizzes and tests, we're always going to assume this is true, but you may see a problem dealing with this in my stat lab.